of these are source studies within seismology. So just a brief recap, discrimination. Is it a nuclear bomb or an earthquake or something else? So remember, the waves from a bomb look different from the waves from an earthquake. And generally, we compare the body wave magnitude from the surface wave magnitude to figure out if it was an explosion or an earthquake. They also give different moment tensors or focal mechanisms. And the waveforms just look completely different also. So this is three-component record. So this is a WWSSN. I think, is that right? Is it a seismographic? Is it a WWSSN station in China? Okay, I think so. From a nuclear test in North Korea. So this is the nuclear test. This is what an earthquake looks like at a similar distance, and this is what a chemical explosion looks like, right? So earthquake source people like to look at these raw waveforms and try and figure out what it was that blew up. Does anyone remember the fertilizer plant that exploded in West Texas a couple of years ago? West Texas being a city that's actually in Central Texas. It's not in West Texas. No, okay, that's fine. It was big. Okay, so another interesting question in earthquake processes is how it ruptures, right? So we have all of these small magnitude earthquakes. What makes a small magnitude earthquake different from a large magnitude earthquake? For example, the 1906 earthquake, was that a magnitude 3 that just got lucky, just didn't stop rupturing, just kept going? Or was there something different from the very beginning about the large magnitude earthquake that ensured that it would keep rupturing? This is actually not something that we know yet. Understanding this would greatly improve early warning for large magnitude earthquakes, right? If we had a magnitude 8 earthquake on the San Andreas Fault, it would take 60 seconds for it to rupture. If we could tell from the beginning, before it even got to a magnitude 8 earthquake, that it was going to be one, that would be ideal. Still unsure whether or not it's possible to do that. Okay, are there any questions about source studies? Okay. So we'll also now talk about structure studies. So how do we know what's inside the Earth? I'm posing this question to you. Yeah. Yeah, so we know that the Earth has a liquid outer core because S waves don't travel through this outer core. What else? How else do we know? Does anyone know what the radius of the Earth is? How far it is from here to the center of the core? 6,371 kilometers. The deepest hole that has ever been dug was 12 kilometers. And that was actually the Soviets digging a hole to see how deep they could dig a hole. So we can't get down to the mantle. How do we know what's in the mantle? We have volcanoes. Volcanoes presumably bring up some stuff from the mantle, and we can use the lava that comes out to try to understand what there is. But the volume of what comes out of volcanoes compared to the volume of the center of the Earth is tiny, is minuscule. So how do we have any idea what's going on down there? We have indirect probes. One of them is potential fields. So we can use something like gravity or magnetism to figure out, what if we have some object that is under the surface, it might vary these potential fields a little bit. But these are hard because the problems are not unique. So you could come up with any number of situations inside the Earth that would give you the same surface observation, which is kind of tough. Electromagnetism. We can use electromagnetics to see deep within the Earth, but the deeper you go, the less clear the images become. And additionally, under certain parts of the Earth, particularly where people live, magnetic fields are dominated by people and things that we do. And then the last one is seismology. So, earthquakes set off waves. They're like sound waves. Some of them are like sound waves. They go through the Earth, and we can figure out, if we know where they started and where they ended up, and when they started and when they ended up, then we can predict sort of how the wave traveled through the Earth. So here's the basic idea of structure studies. You have an earthquake, creates waves, goes through the Earth, and then it arrives at our seismometers. And each one of these things will determine a little bit what the waveform looks like, right? If we have earthquakes that are maybe the same magnitude, maybe on the same fault, but they just have a slightly different rupture, that could produce different waveforms. Generally, people who study Earth structure believe that these are simple, which is fine. And then seismograms also, if you have different instruments that are recording these waves, they could record them in slightly different ways. But we have ways of removing this, and so we can get at the Earth's structure by tracking these waves as they propagate through the Earth. And this is what we call seismic tomography. So seismic tomography is kind of just like a CAT scan, but rather than using EM waves, we use seismic waves. So this is the basics of seismic tomography. You have an earthquake, you know where it is, and you know when it happened. And all of these triangles are little stations, right? So the forward problem would be, if I know where the earthquake is, can I then send out waves to figure out when they would arrive at these stations, right? And we can predict them knowing something about the geology. So we do. We say, earthquake happened here, the waves move so fast, and then it's going to arrive at this station at a given time. Say it's 100 kilometers, P waves go 5 kilometers a second, then it'll arrive after 20 seconds. 20 seconds after the earthquake. Pretty easy, right? So what happens if the wave arrives late, 21 seconds instead of the 20? That means that somewhere along this path that the wave took, it went slower than we predicted it would, right? So if we record, so then say this station, it arrives early, so then it probably traveled somewhere along that ray path faster than we predicted. So if we take lots of stations and lots of earthquakes, then we can, did that do anything? I don't think I did anything. Then we can figure out these slow paths versus these fast paths, and lots of stations and lots of earthquakes, and a pattern emerges from which we can construct an image. And this image tells us, in this sort of red shaded region, the waves travel slower than we expect them to. And in these blue regions, the waves travel faster than we expect them to. So that's the basic idea. So then the question becomes, what do the red and blue colors mean? Other than obviously the waves traveling slow or the waves traveling fast. Physically, why does a wave slow down, or why does a wave speed up? There are a couple of things that can make waves travel different speeds. One is temperature. If you increase the temperature of a rock, the rock begins to soften, and that means that seismic waves are going to slow down. But additionally, if you have different types of rock, or if you have rock and water, say, the waves are going to travel different speeds through the different chemistry, through the different materials. So one of the problems with seismic tomography is we actually can't distinguish between these two. All we get is the red and blue, and then we have to make some kind of interpretation about what we see. So are there questions about this? No. Okay, so I'm going to talk a little bit about something that I find interesting. It might have sounded like I was taking a couple of cracks at structure seismologists, but I am one, and so I guess it's okay for me to make fun of myself, right? So I study the Pacific Northwest of the United States, and it's a particularly interesting region because we've got this Juan de Fuca plate. We know a subduction zone is along the Pacific Northwest, right? What is this subduction zone called? Cascadia, yeah, the Cascadia subduction zone. Yeah, so we know there's a subduction zone. We know that large magnitude earthquakes happen there. We know that there's a range of volcanoes that are a result of this subduction zone. But sort of the entire western United States is really, really confusing because a lot of weird stuff has happened there. But the point that I like to make is that this is what the magnitude 9.1 Sumatra earthquake looked like. This is the rupture patch, what ruptured in the in a magnitude 9.1 earthquake, and it fits pretty nicely inside the Cascadia subduction zone, right? So large earthquakes have happened. Large earthquakes will happen again, and we should learn as much as we can about it beforehand. Okay. So another interesting thing about the western United States is that how many of you have been to Yellowstone? A lot of people. Good. Yellowstone's pretty cool, right? What is Yellowstone? There are lots of geysers. Why are there geysers there? Because it's hot. It's a hot spot, yeah. So a hot spot, when we say it's a hot spot, we mean it's a giant volcano. Nova or something likes to use the term supervolcano. I think they invented that term. But nonetheless, it's a supervolcano in that it is a really, really big volcano. And so we've got a magma chamber that's heating the water. One of the interesting things, though, is that we can look at the geology and trace where the Yellowstone volcano was back with time. So 4 million years ago, the caldera was here, and 11 million years ago it was here, and 13.8 million years ago it was right there. So the North American plate is moving this way down to the southwest at about the speed that we see this hotspot track moving, which means that whatever is supplying this volcano with magma isn't moving, right? The plate is just sliding across the mantle on top of it. Yeah, so the western United States has lots of interesting things, one being a hotspot, one being a subduction zone, and then sort of the fact that they had to have interacted with one another. Okay, and then this is the Columbia River flood basalts, which, you guys mind if I show a YouTube video? Good. I like this video because it shows you what a mantle plume kind of looks like. I'm going to need to connect to the internet, aren't I? Hopefully this is... Okay, so there's a candle here. There's a bunch of ink in the bottom of this thing. And so this is what a mantle plume looks like in the mantle. It's sort of this hot stuff that rises when it gets to the surface, it flattens out. And so if we imagine that being lava, what happens to it when it gets to the surface? A lot of lava erupts over a very short period of time. That's what the Columbia River, that's what some people think, me being one of them, the Columbia River flood basalts are, is you have this massive amount of magma that comes from very deep within the mantle, and then it erupts in a massive amount of lava. I really hope this starts from the right side. Good. So, a number of interesting things happening in the Pacific Northwest. So what do I do then? This is a tomographic image of the Pacific Northwest. What do you notice, other than just sort of random blue and red blobs? I'll direct your attention to this. What do you think this red guy is? It's Yellowstone, right? It's hot. You have stuff that's melted. So waves are going to slow down as they approach this region. So we can see that Yellowstone is indeed very warm. And we can see that this increases dramatically, that it continues dramatically with depth. This is at 200 kilometers depth. So even at 200 kilometers, you can see that Yellowstone is hotter than the stuff around it. What do you think this big blue thing is? So this line right here, oh, I can't hold my hand that still, but this line, what is that? Yeah, that's the Cascadia subduction zone. So this plate is moving that way, toward North America. When it hits North America, it gets pushed underneath, right? If we go back to this picture, this would be, it says Nazca, but this is what the London plate looks like. This is what the North American plate looks like. And so the plate gets pushed down underneath North America. So if we were to take a slice right here, you would see that plate descending through that slice. Would you expect the plate to be warmer or colder than the material around it? It should be colder, right? It's been sitting on the surface of the Earth for 40 million years. So this is going to be much colder than the mantle around it. So this is what we're looking at. This blue thing right here is the cold subducting slab. It's descending into the mantle. So we can see that with these tomographic images. Then you may wonder, well, what's this red stripe? That's a good question. We don't know. Should be really interesting, though. Stay tuned. So I'm going to show a couple of interesting little 3D slices. So again, this is a little confusing because we don't really have a map except for this one. So California is here, and this is Nevada. North is that way. And we're going to look at these slices from this direction, right? So we're looking south to north at sort of like toast coming out of a toaster, sideways on. Okay, so this is below the subduction zone. We've just got slow velocities to the south of the triple junction. We've got this fast stuff underneath the oceanic mantle. As soon as we hit the subduction zone, though, we've got this really cold slab descending through a relatively warm mantle. And then there's this question mark over this blue thing because we don't really know exactly how to interpret that, but it's there anyway. But if you move a little bit farther north, the slab appears to have been detached. So what might have caused this slab to break in the mantle after having been subducted? So we continue to see this broken slab. There's a slab tear of some kind. And then if we go far enough, we get the Yellowstone caldera. So the Yellowstone caldera, this is the plume tail coming down into the mantle, supplying magma for a very long period of time, millions of years up to the Yellowstone caldera. And then one to the north, that's the plume again. So perhaps this plume caused the tear? Not totally clear. This is an interesting slice where we've got it going along the subducting slab. So you can see that this is one big continuous cold thing that goes all the way down to about 500 kilometers depth. Pretty deep. Great. So this is what regional tomography looks like. We can figure out what's going on beneath a particular area of the globe. So regional tomography is not the only kind of tomography. We have other people in the department who do global tomography. They look at the entire Earth all at once. And so this is at 100 kilometers depth. Where does this red stuff seem to follow? Like, I already put up the answer. I shouldn't have pointed that out. The red stuff seems to follow the ridges, right? So the ridges, you have stuff from the mantle that's moving upward and partially melting as it reaches the surface, which is going to slow waves down. And then even if you go down to 200 kilometers depth, you have these cold continental roots sitting below the continents. These are the oldest parts of Earth's crust, and they go down really deep. Are there any questions on global tomography? Are there any questions on anything we learned today? Yes? So the question is about the final. The question is, there's a third midterm and then a final. Yes, they'll be handed to you at the same time. Is the third midterm as long as the first and the second? Yes, it should be identical. And then there will be another test that is the final that happens at the same time. But then the final lasts longer than the... You have, what, 2.5, 3 hours for the final exam? So one of them should be for the... So the question is, it doesn't seem like we covered as much material. We'll find a way to get an exam out of it, though. Yes? Okay. You will, I don't remember exactly how it works when you get here, but there will be 2 booklets and 2 answer sheets when you arrive for the exam on December the 17th. You will either get both of them at the same time, and then you'll turn both of them in, or you'll be handed the 3rd midterm, and then you'll take that exam and hand it in, and then we'll give you a second booklet that is the final. But they're going to be of similar length, and so you should plan on taking a test that is twice as long as one of the midterms. And don't think about it as 2 tests, just think about it as one test that's twice as long. And one of them is going to focus entirely on the 3rd section. That's probably the best way to think about it. The format should be the same for all of them, yeah. Hope you had a good Thanksgiving.